Hello, once again. This is Mr. Meyer coming at you from the plush studios of Way Happy, and we're going to talk about the dot product of vectors. Now, the dot product is fun because in physics it can help you deal with force and work, and we'll probably get into that in class. But let's at least get through the mathematics that you get to do with dot products. So, vectors can be multiplied two different ways. One way is called the cross product. Now, the cross product is not something we're going to do because it just talks about a vector that's perpendicular to two other vectors, and we're not going to worry about that right now in this three-dimensional space. But we will talk about the dot product, which is a number that represents the scalar product of two vectors. In other words, it's kind of like it multiplies the magnitude of the two vectors and the angle between them, and it gives us a number, and that number actually turns out to be very useful. And so as you can see down here, the definition of the dot product, that definition is quite simple. You will take two vectors and notice the formula right here. That formula for dot product. So that u dot v, that is the dot product. It means dotting two vectors together. Notice they're both bolded vectors. You will just multiply their I coordinates, and then you'll multiply their j coordinates, and you'll add it together. And it's that beautiful. It's a simple mathematics work that actually gives us something nice. So once you do that, you will have a scalar, and that scalar will be the number that we're after. Now, there's some properties of the dot product, and just so you know that you can read those. Number one, showing that it doesn't matter which way you dot the two vectors together, so that's cool. Number two, look at that. That's the magnitude right there, and it's if you really think about it when we do it, it makes sense. But if you dot the same vector with itself, you will get the magnitude of the vector, the squared magnitude. So you square root that and you can have the magnitude. Anybody dotted with the zero vector is going to be 0. And that kind of makes sense too, because you're multiplying by 0 and then adding it to 0, you're going to get 0. So let's go ahead and talk about this first example. Let's go ahead and find the dot product of u and v. So I define vector u as 4, 5, and vector v as -3, -7, and I want you guys to find that dot product. So all the dot product is you will go ahead and multiply u i's term with v's i's term. So 4 times a -3, and you will add that to 5 times a -7. 5 times a -7, and in essence, that's your dot product. You just clean it up. It's -12 minus 35, which is -47, and that is your dot product for u and v. Plain and simple. Now, here's the little fun with the dot product, but you may or may not find it thrilling. The dot product, that property number 2 up there, like I said, gives us another way to find the length of a vector. So say somebody wants you to find the length of that vector. You already know one way, so don't forget that. 5 squared plus 12 squared square rooted, you get the magnitude of the vector. But just if you were curious, you could just do this vector dotted with this vector. So you could do 5, -12, dotted with 5, -12, and that would also get you the magnitude. Well, here's why, right? 5 times 5 is 5 squared, so we'd have 5 times 5 plus a -12 times a -12. In essence, you're really just doing squaring each one, and you're getting 25 plus 144, which would be 169. Now notice that scalar is the magnitude squared, so if I just square root that 169, I get 13. That would be the dot product that would help me find the magnitude of that vector. And you can still use your old magnitude vector. I just wanted to show you the dot product, how it would also work. And so kind of interesting. All right, let's let you try a dot product, and I'll see you in a few. Nice work. And I told you, the dot product not too scary. Now let's talk about something fun with the dot product too. You can use the dot product to help you find the angle between two vectors. So if you look at my drawing right here, we got vector v and we have vector u, And if we wanted to find the angle between those two vectors, we could use really the law of cosines. And if you do the law of cosines on this triangle, you will come up with this beautiful formula that you see in the green box right here. And so if you want to find out the angle between two vectors, I encourage you to go ahead and do the law of cosines and have some fun, or look at the book, they prove it in there. But if you want to see where this is derived from, it's there. But how do we use it? So we're just going to go ahead and use this formula, and we're going to talk about, all right, I want to find the angle between these two vectors. I want to find the angle that is between this vector and this vector. And so I'm just going to go ahead and use the formula. Now look, there's a lot of parts. There's the u dot v part, which we already talked about is not too spooky. So that would be -4 times -1 plus -3 times 5. So that to me looks like 4 minus 15, which is -11. So that u dot v is -11. That is the dot product. But look what else we need in the formula. We need the magnitude of u. So if I want the magnitude of u, then what I would do is I would square that. So 4 squared plus 3 squared, all square rooted. So 16 plus 9, which is 25. It might bother some people that I drop the negatives, but if they're going to be getting squared, the negatives are going to disappear anyway. And so the magnitude is 5 for u. The magnitude for vector v, because I should put my vector symbol since I can't bold very well. The magnitude of vector v would be -1 squared. No, look, now I'm using it. Plus 5 squared. So what is that? 1 plus 25, or the square root of 26, which I can't simplify. And now I can use this information in a calculator to find out what that angle is. The formula is the angle is the arc cosine of u dot v, so for us, -11, over the magnitude of u, which is 5, times the magnitude of v, which is root 26. And now I will just grab a calculator and type it in. And notice I had it ready for us. As I typed it in and I hit enter, I get it's about 115.56 degrees. So I get that the angle is about 115.56 degrees, and I jump up and down. That's what I found it out to be. Now sometimes I'm always curious, right? The back of your mind, you're like, I wonder if that was really 115 degrees. Let me turn on some graph paper here, and I will try to draw some axes, which even with copying straight lines, I'm probably going to be miserable at. And let's just look at the visual. Vector u was -4, -3. So I'm going to do that in red. So -4, -3 would be sitting right here. Remember, it comes from the origin. So there is your vector. That's we call vector u. And then I want to do vector v. I'll do that in blue, say. And he's -1, 5. So -1, 1, 2, 3, 4, 5. He's right there. And he is vector v. Now, is it conceivable, believable in any way, that that angle between the two, this angle right here, really is 115 degrees? And I'd say yeah, right? It's definitely more than 90, and I'm feeling pretty good. So that is just a little visual there of what you can see, that this formula is actually pretty handy. All right, here's a little vocab for you too, orthogonal. Really similar to perpendicular. If vectors are perpendicular, or we're going to say orthogonal, then their dot product would be 0. So if you do a dot product and it equals the number 0, notice up here my dot product was -11, the vectors weren't perpendicular. But if it ever does equal 0, then those vectors are called orthogonal. Now, it really means the same thing, except for they had to make a caveat, right? Is that the 0 vector cannot be perpendicular to anybody because he has no direction. So how could he be perpendicular if he doesn't go in any direction? I wouldn't be able to see what he's perpendicular to. However, his dot product with any vector will always be 0. So that's why that 1, 0 vector is the reason why we can't use the word perpendicular, so we use the word orthogonal. And there you have it. Another vocab for you. All right, let me give you a quick one, and I'll see you in a few. All right, and nice work again. And now the fun part that every math geek and physics geek loves is how about projecting one vector onto the other? And you say, what the heck are we talking about? Well, we're talking about this vector u right here, and it's acting with another vector here. And I want to know how much work or force both of those vectors are doing together, but I want to do it in one direction, so in that PS direction right there. So what I do is I project what math geeks like to call project that vector u onto this other one. So kind of that's where that red line comes in. I'm taking this u vector and I'm seeing how much work it's actually doing horizontally or in this direction. That looks kind of horizontal. And I'm projecting it just onto there. So how much is it actually contributing? So really I'm just finding one of the parts of that vector. Remember that this vector u could be this piece plus this piece, right? And if it's those two pieces added together, I'm just kind of curious, what is this horizontal piece or this PR piece? How much is it doing in that direction? And that's all projections are. And they come in really handy in word problems or in physics when you have you're trying to hold something from rolling down a hill, or you're trying to find how much force or weight something is. Um, we will do those in class, but I want to at least have you look at how to project one vector onto another. So here we go. Let's find the projection. The way it's written right here, you can kind of see, is this is projecting u onto v. So we are projecting u onto vector v. Vector v is this long vector that kind of broke up into PR and S. And we're going to just project u onto v. So it's a dot product once again. And then you have down over here the magnitude squared. And then you multiply that with the vector you are given. And that should get you the projection of u onto v. So let's go ahead and try this. Again, maybe I should draw ourselves a little picture so it at least looks somewhat neat. So here is my axes, which look like that should be enough. We will call u 2, 3. So 2, 3 is right there. There's one vector. And then 6, negative 1, I'll do that in blue. 6, so that's 3, 6, negative 1 is right there, and that is my v vector. And I want to project u onto v. In other words, how much work is the red one doing in the direction of the blue one? It is helping. It's moving it to the right a little, but how much is it actually helping? And so that's what that means by projecting. So you would, really what you do is you draw this perpendicular line to the blue one that goes straight up and hits the red one. And I want to know, how long's that side right there? How much is that actually happening? Doesn't look like much, does it? But let's see what it is. So let's find out that projection. So we'll call this guy u, we'll call this guy v. We're going to project u onto v. And if I could spell that right, that'd be a lot handier. So I'm going to project, u onto v. So that is u dotted with v, and that is v magnitude squared. And then we're just going to multiply that with vector v. All right, so let's see the dot product. So u dot v, let's figure out what that is. That is 2 times 6 plus 3 times negative 1, or 12 minus 3, which is 9. So we have 9 over, now the magnitude of v. Let's see what the magnitude of v is. 6 squared plus 1 squared, all square rooted. So that is 36 plus 1 is square root of 37. But that gets squared, so that is just 37. And multiplied with vector v, which is 6 comma negative 1. So you just distribute that little guy through there, and you get, what is that? 9 times 6 is 54 37ths, and negative 9 37ths. And that vector is that little vector right there, that little projection. He is right almost 2, and down not much, right? And that is how big that vector is. And so that is called the projection of u on to v. And now let's go ahead and finish up the last part of this that says write u as the sum of two perpendicular vectors, orthogonal vectors, which one of them is the projected vector. So in other words, here's our little projected vector that we found, and then who's perpendicular to that? This guy right here. And can you find that vector and tell me what u is written with those two added together? Well, it's kind of not as tricky as it looks, right? We already got the projected vector, that's right here. Now we have to add some other vector. I'll just call it x and y because I can't think of anything else. And added together, they should equal u, which is 2, 3. So now I can figure out what x and y are just by doing a little bit of simple arithmetic, right? That other vector, xy, would be vector 2, 3 minus this gross one that I have, and I will now have my answer. And that would be 20 over 37 for the first one, and 120 over 37 for the second. And so there are your two vectors. There is this vector, which is the green line, and the projection vector, which is this guy right here, the highlighted yellow. Those two vectors, those two perpendicular orthogonal vectors, would add up to vector u. And that's going to be the part that we're going to use with all the physics problems that we do. All right, take it easy. I'll see you in class, and stay happy.